Hi, my name is Manuel Benz. Welcome to my talk about heaps and leaks, or how heap snapshots improve Android taint analysis. This work is a joint effort between these excellent researchers and myself. Taint analysis is a commonly used mean to find vulnerabilities in software products. It aims to detect sensitive data flowing from a source to not so preferable sink. Static taint analysis usually yields a very high recall, but also oftentimes suffers from a comparably bad precision and scalability. In particular, the precision of static analysis of languages with dynamic dispatch usually heavily depends on the precision of pointer analysis. Recent research by Crash et al. Has shown that incorporating data from heap snapshots can be either used to increase the soundness of static pointer analysis by augmenting the static pointer information with the dynamic one, or to increase its precision by restricting static pointer information to the dynamic one. Heap snapshots essentially are records of dynamic pointer information at a given time of app execution. In our work, we build upon the work of Crash et al. By also investigating the questions: how client analyses are affected by the heap snapshots based pointer analysis, how many snapshots are required to yield the best results, when should snapshots be collected during the application runtime, and last but not least, can we find a middle ground between high precision due to restricting the static pointer information and high recall due to augmenting static pointer information. For that, we designed the blended tainter analysis Heaps'n, where we used the pointer information from heap snapshots as upper bound for the pointer analysis of Java fields. Thereby, we trade off recall from the static model for increasing precision through restricting the static pointer information to only dynamically seen objects. Our design especially enables three different modes of execution: separate heaps, where multiple snapshots are used with independent analysis runs and the results of each run are merged together; merged heaps, where the heap data of multiple snapshots is merged together to gain a single, slightly over-approximated snapshot; and static fallback, a mixed mode where we fall back to static pointer information for fields for which we do not have any dynamic pointer information available. This mode is independent of the other two and can be freely combined with them. For our experiments, we took 49 of the 200 most downloaded Android apps from the Google Play Store. We manually explored the apps on our smartphones and took a heap snapshot after each user interaction with the app. Thereby, we gathered more than 2,300 heap snapshots. For our experiments, we needed a ground truth to compare against. Therefore, as part of our work, we proposed Droid Macrobench, a real-world taint analysis benchmark comprising 157 taint flows labeled for feasibility of 12 of the 49 apps, effectively yielding 79 feasible and 78 infeasible flows, which is basically 50-50. In our study, we asked and answered 4 research questions, which I am now going to discuss. First, how are the precision and soundness impacted by using heap snapshots as an upper bound for the static analysis? By measuring against Droid Macrobench, we found that using the separate heaps approach and the merged heaps approach, the results only vary slightly. Both approaches yield a very high precision, but for a huge cost and recall compared to the purely static analysis. Second, how do precision and soundness change when using the static fallback approach? Using the static fallback approach, where we take a static pointer information for pointers that are not present in the heap snapshots, we measured a precision of about 77% and a recall of 68% with the merged heaps model of all collected snapshots. This is an increase of about 26% in precision and a decrease of about 31% recall compared to the fully static approach. The static fallback approach thus yields a good trade-off between precision and soundness. Having more than 2,300 snapshots for 48 apps collected after each user interaction, we further propose the following heuristics to choose from those. First, where the first snapshot is taken after the app has started. Last, where the last snapshot is taken that was made during an execution, unique activity, where the last snapshot conducted before leaving each Android activity is taken, and all snapshots. Looking at all data points, we can generally say that using heap snapshots in any of the proposed configurations increases precision and reduces recall compared to the pure static analysis. Looking at the results for merged heaps, it can be observed that taking more snapshots gives a better recall but also lowers precision compared to taking less. For the static fallback approach, the picture is a bit different. Here, unique activity performs better than taking all snapshots. We conclude that when and how often a heap snapshot is collected has an impact of about 16% on precision and 13% on the recall, with the best overall results being achieved with a single snapshot per activity and the static fallback approach. In our paper, we also inspected the impact of the different modes and snapshot choosing heuristics to analysis performance and resource consumption. We leave the details about this part to the interested reader of our work. To summarize, we proposed a new middle ground between precision and recall by using pointer information from heap snapshots and falling back to pure static information where no dynamic information is available. We introduced Droid MacroBench, a real-world Android app benchmark comprising 12 apps with 157 labeled Taint flows. We investigated how heap snapshots should be incorporated in a static analysis and at which points they should be gathered. We found that if precision is critical, a single heap snapshot taken at the start of an app might be the strategy to choose. In case recall is critical, however, a purely static analysis or an augmented version still yields the best results. Finally, compared to the fully static approach, static fallback achieved the best trade-off between precision, recall, and runtime performance. It heavily reduces analysis time and memory consumption, and furthermore, it increases precision by about a third while losing less than a third recall on average. This results in the overall best F1 score of 0.77. Thanks for your attention.